Yes, good evening. Uh, Welcome to the 10th week of the session for the course of a statistic for biomedical engineers. If you have some doubt and all, please ask. Can you please confirm that my voice is audible? Okay. Uh, Welcome to the 10th week for the live session for the course of a statistic for biomedical engineer. Uh, I am MD Asid Raza, PMRF fellow and in Tiruchirappalli. And this is some background of myself that I'm currently pursuing PhD from in the Department of Mechanical Engineering at Tiruchirappalli. And I have completed my master in machine design from the CIT Trivandrum. And I'm the PMR fellow. That as a PMR fellow, that I'm handling this course as a TA, teaching assistant for this course. So that we have seen in the last 9 week that we have discussed started with the this course is actually for the statistic. It's a foundational course for the machine learning that if you go that more deep and on. One more thing, like if you have any doubt and all, so we can discuss till the last class and then we'll go ahead slowly. If you have any doubt, please ask. Okay, so hopefully there's no doubt. If you have any doubt, that you can ask anytime. So that we will discuss like just a brief that what we have discussed in the last 9 week. We have started the first course that we introduced what is the statistic and then how it's going to use in the biomedical. So it's came or it's we have named as a biostatistic and all. After that, what is the purpose and application will be there. So application we were having like something if we have to make some drug delivery or any instrumentation like their efficiency or efficacy, we have to check it out whether it's correct or not. So whether we are able to see any differences or not, and or either any drug that we are going to administer for any particular disease like fever or any viral flu or COVID flu and all. So so we can't administer the drug to the whole population. Like it's in the world we have 3 or 4 billion people are there, but so we can't deal with that or we can't administer all drug. And so we'll take some sample. So based upon the sample, we are going to make some sort of observation or inference, and we'll tell, okay, this drug might be useful or having better efficacy or efficiency and all based upon the WHO guideline and all that we can see. So it's something that we are going to take number of sample and then we'll do some testing that called statistical testing and all. So to jump into that, we have to know what are the things that are going to come into the picture. First one that we have to discuss more about the probability, because something when we talk the statistics, so we have to talk in terms of confidence level or in terms of that error probability and all. So we have to that we should know what is the probability and all. So in that also we have seen like a theory of the probability. Then we have discussed the what are the distributions we have, like a Poisson distributions. Then we have binomial distributions we have. Then we have the normal distributions was there. So once we came, then like we were having descriptive statistic and all. Descriptive statistic is something that we have to talk about the numbers description. Let's say that we have the samples are there. Samples is there, but samples like what is the mean, what is the mode, and what is the that some sort of variance or that the deviations we have. So that we have to know it. So that in that wherever there is no talk about anything that we have to infer or to make conclusion, so that will comes another description. Only it will give the some sort of idea about the data. It will not give whether it's good or bad or it's a yes or no or either one or like a zero, but it will give us some idea. Okay, this is the 10 number of people are there, so average age of the people is this much or average weight of the sample is that much. So it's something they will give the properties or characteristic of the data and all. That's all. Then we have checked. So these are the description. Then after we check about the variances, like let's say we have taken the samples, like whether it's any, what are the variances? If the variances are too high, so that we don't have the consistency in the data or the sample we have took. So in that case, the error will be high. So, but we'll not able to come up with any conclusion or anything. So we have to discuss that thing also. Then we have checked with the sample statistic and then came to the inferential statistic. Inferential statistic is something that we have to infer about based upon the probability or the occurrence of the event that anything is happening and all. So for this case, we were having started with the central limit theorem. Central limit theorem. It's something called, it's a universal that we are going to start first, and we'll check with the mean differences and all. So here we don't have any like limitations of the number of samples and all. We can go the 100 and like 20, 30 and all. Then we talk about the confidence interval, like what will be their size, like that is the upper limit and lower limit is there. And we started with the hypothesis testing. Hypothesis, that's something we are going to tell about, like first we have to assume, okay, there is a status quo. Let's say I have taken two sample. Let's say for a soil, fertilizer is there. We took one fertilizer, second fertilizer, then we took the third one fertilizer. If the in the fertilizer, we'll say which fertilizer having better efficacy. So that is our research question. So whenever we are going to discuss anything in the statistic, so first we have to decide like what is our like question, like that is the that I need to answer, or something that we have to check in terms of, let's say, for the quality control in terms of the industry. They will say, okay, I'm going to apply this particular method or the Togachi method and all. But happening like whether my cost got reduced or not, or my say that what you can say efficacy or efficiency of the machines like it's good or not, or we'll say like the product finishing is good or not. See, something that is that something that I have to answer it based upon the statistic. So what will be the status quo? Status quo is something that we have to assume there is no much differences there, or like there is no difference will come. So means for the industry that we have took one sample, second sample, third sample. We'll say there is no much differences are there, but they were having some different groups was there. One group, second group, third group. First group, let's say they have the diversity differences was there. Second group that comes under the different loading or career different diversity was there. Third, simply we took it out and that we have check it out. So what is the null hypothesis? Null hypothesis is something we call status quo. You will say there is no differences in the three groups and all are there. So what will be the alternate? When we are saying either yes or no, like we'll say there is no difference. So alternate will be automatic. It will be there is a differences are there. So in that case also, what we have like alternate hypothesis. So we have like two-tailed test. When we'll say okay, mu1 is not equal to mu2, we'll tell like this. Then second one we have a one-tailed test. Either mu1 is greater than mu2 or mu1 less than of mu2. So in that we have to deal with the two cases. So alternate hypothesis, the alternate will be like there is a whenever we'll say any change of differences, or there is three possibilities are there. One, we'll say there is no differences are there. That is a status quo that will define as a null hypothesis. Second will be that we are saying okay, there is a differences are there. So we'll tell mu1 is not going to be mu2. So that is our null hypothesis, and will not tell like which one is more or which one is less. So it's called two-tailed test. It can go either way. That we are not specify it and all. Then we have either, let's say it's going to mu1 greater than mu2. Then mu1 less than of mu2. So that will take. Then we came across the large sample test. So in that we have discussed based upon the central limit theorem and all. Then we came across the p values. What is the p value? That is the probability of the error that is going to happen, or like based upon that, we are going to say that much of things we can accept. Beyond of that, we'll say there is no significant differences are there on all. Then we came across the then we came across the t test. T test is something when the number of sample it got reduced to less than 30. So in that only that we can see in t-test distributions also we were having different types of t-test, were the pair t-test, independent t-test. and then check for the variances also, like it's a pair and unpaired, we have to check it out. Then we came across the type 1 error, then type 2 error. Type 1 error is something that we are not able to we were not able to reject the hypothesis. And then second type 2 error, that was not the null hypothesis was correct, but what happened, we have assumed that okay, that's not happened, so it's a it's a limitations and all. Then we came across the power of the test. Power of the test is something that we have a confidence level, we can say, based upon that we are able to say. Then chi-square distribution. Chi-square distributions, once whenever we have to fit or fitness of the any that model. Let's say some test or some of data set data says that is set is there. We have to fit to the particular model. Like let's say we're going to fix for the normal distributions. Let's say we are going to fix for the binomial distributions and all. It's something like goodness of the test, goodness of the fit will tell. So in the case of chi-square test, we'll check whether the data is going to fit for the anything or goodness of the fit and all. Then slowly we, because till now we were discussing more and more into the that mean differences and all. But the thing is that mean alone will not give the clear picture, or the mean is not able to give the better perspective of the statistic and all. So then we are going to check with the anyway the that the idea will be any of the sample their mean differences are there or not. But the thing is that the method will change. Till now we have checked with the only methods, and in that the mean was the main calculation. So now we are saying okay, mean will not give better picture because it sometimes it will act like as a bias. Let's say if one sample having that the very low number, second sample having that higher numbers, so what's happening that the difference will be more. So what will happen due to the bias, they'll be able to say that we have the more pictures, that's the more differences are there. So but will not able to tell that the conclusion will be not good enough. So what we'll do, we'll check with the variances. So for that we have the test F distributions. Okay. So in the F distribution, what we were able to do, we were able to do only with the two groups. It's an extension of the t-test, but the thing is that the calculation or the methods was something called variance we have calculated and then came across. So in that also we have a F ratio we calculated like whatever the maximum variance by minimum variance was there. So now the so till now that we were having the idea that we are going to check with the two groups. But in the case of real-time applications, we'll be having three group, four group, and five group, and six group. In that case, we have to go with the ANOVA. So we have to move to the ANOVA. So for that also, we'll be having some sort of assumptions and all will be there. Then we are going to ANOVA is an actually extension of the F test only. The only differences will be there that we are going to check with the more two, three more groups are there. So then we have checked with the treatment and error in the square. Then we have solved some problems. And slowly we have discussed about the variances and the correlation between them that the variable. Then LR we have seen like that the linear regression we have seen. What is the R square statistic we have seen also. Then we came across like that the linear regression simply that the linear regression is actually works on y is equal to mx plus c. But what will happen in the case of more that the application it's in the real time applications and all, it will not like a simple regression, like that's not going to behave like y is equal to that the y is equal to mx plus c. It's something will be the called that the null that's a non-linear functions which comes into the pictures and all. So for that we have went to the logistic regression. So logistic regression, it's a logit function is there. Only thing that will deal with the that the logarithm function is that we are going to instead of going with the y is equal to mx plus c, we'll go with the logarithmic function. It's a sigmoid function. Sigmoid function, and that's the log function actually. When we check the likelihood function is the probability of the things or event that is going to happen. Then we have fit the ANOVA using the linear regression also, because the linear regression we have the continuous line will be there. What we have done, so we have done the grouping, a homogeneous group we have taken. We have done the grouping, two, three groups. Then we similar way we have derived the ANOVA also. Okay. And in the case of logistic regression, we'll be having either 0 or 1, either yes or no. But in the case of linear regression, that we have to in continuous line will be there. So after that, that the idea is going to start with the two-way ANOVA. But before that, we have to check with the like how to design experiments and all. So introduction to blocking. What's happened? Like we were having one, two, three, four groups are there, but we were not checking that their interactions and all. So we came across the design of experiment. So today we will start like that the last class we have seen more little bit of RCBD like that the randomized complete block design, and we have solved some problems also. So today we'll again revisit that problems and we'll go slowly and we'll solve some problem based upon the Latin square design and then that the Gracio Latin square design and we'll check with the interactions and introduce the two ANOVA also. So can you anyone tell like what is the purpose of the design of experiments? What is the purpose of what is the whole idea of the design of experiment? If we are here, can you please tell? Okay, so if we talk about something that a system or process, it's going to be in the operation and part of the learning process. It's going to be like how the system and process work. So if any system or operation, like let's say we have any system, let's say a company they have to open and they have the manufacturing setup is there. So how they're going to plan how that how they're going to make the product to be happen and all. It's just all part of like we have to do the conduct the experiments. For that we have to conduct the experiment on the system. Like that let's say I have a company of to make the shoes. So to make the shoes, we have to conduct the experiments. Or if that is going to beforehand, that the R&D sector will come into the picture. So they will take multiple times of experiments with the multiple different that the material they will take and then they will check with the things. So observation of the system or process, observation of the system or process that lead to the theory and hypothesis about the what make the system work. So I told, like in the design of experiments, something that we have to design. That is what factor will comes into the picture. Which factor is that we can control, which factor that we can't control, or how that any methods or any design we can apply that we can control the like that we can limit the uncontrolled factor and all. So for that we have to design the experiment very careful manner. So but experiment that is type described above are required to the demonstrate that the theories are correct. Whatever we are going to make the hypothesis, I'll say, like let's say I'm going to, I have soil, I'm going to put fertilizer 1, fertilizer 2, fertilizer 3, fertilizer 4. We'll take trial 4 experiments will take, and every time once we'll do the experiments, that will be the baseline. That is the things we have taken care as a baseline, and after that we have changed the composition. Then we have done the again experiments. What's going to happen on the soil? Whether that our paddy or wheat, like whatever the crop we are taking out, it's coming like good or not. So that is the first trial. Then we took again we changed the composition. Then we took again second trial. Then we again check with the soil testing and soil properties and all. Whether it's got change and all. So whatever that hypothesis we kept, theories or hypothesis we have designed. So whether it's coming or not, let's say I said like if I'll change in the fertilizer one, a chemical I'll change that is 10%. So it's going to be like change some that soil that the crop is that the yield is going to more. So that is the hypothesis that we have to it should come correct. So that's why so the idea is to we can design the experiments in a proper way so that number of trials should lead that should reduce and the timing should like play with the greater picture because when we talk about the experiment for some time in the case of drug and all we have to do the numerous experiments we have to do 10,000, 500. 300 on a single sample. If you do the testing and if you check as much as possible. So each experiment run is a test. More formally, we can define experiment as a test of series or in which purposeful change are made to the input variable so that we can get some output response, have some different output response should be there. Either it's for the case of drug that the efficiency or that effectiveness will be more. And let's say I'm something if any spray is there that is for something called that the viral fever and all, it should reduce. So that is the things that how we have to run in the continuous way. So if we are going to consider the simple experiment, a simple experiment. So number of questions that will comes into the mind, are these two solutions the only quenching media of the potential interest? Let's say I'm going to take a drug or medicine that I have to take for the fever. So I'll take two sample. So again the question, let's say, are these two is the only that available is there, or we have to take the more and more, or the whatever the in the market, whether we are going to give better results as compared to that the market and all. It's something called brainstorming, whether we have to ask the question by ourselves only, whether the things what we are going to do, it will make the sense for the that the society or not. If not, then it's the so that we don't serve the purposes and all, so that we have to take care of that. Are there are any other factor that might affect the hardness, or there is any other factor? Let's say I'm going to take drug 1, drug 2 for the fever. So we took all the parameters, like let's say the temperature, this one, the composition, that's all we have checked it out. So we have to think like, oh, any other factor comes into the picture that is that we don't, if whether we have the control on it or not, like something that we have to discuss and all. So that should be investigated or controlled in the experiments. So we have to think more and more about the variable that is going to be comes into the picture, whether we'll able to control or not. And then after how many coupons of the alloy testing, or like we'll say like how many times you will do the testing, only one, two samples, three samples and all. How we can change the things so the data will be collections. What method of data analysis will be taken care. It means once we collected the experiments, so now we have to decide which statistical method we have to go with that. If it is going to be less one way of ANOVA t-test, if, whether the our data is going to be normal or non-normal, like something that we have to design. Then after we have to check whether what is the difference or any inference that we are able to make it or not. So if you talk about design of experiment DOE, first one will be the input. Let's say we have taken, then we check with the controllable factor that we can control, that we can vary. For the case of drugs, we can vary the composition, we can vary the thickness or weight, height, or its composition. We can vary it out. But uncontrollable factor will be like something that we don't have control on it. Like let's say for the fever, like we can control the composition or we can change the intensity of their that the material will keep like that the device or something called drug will change it, composition will change. But uncontrollable is something, what is the age and all, something like it's going to be like something we don't have control over it. That will be automatically it will be there. Then based upon the then we came across the output. Then we'll check with the statistic will do. Then we'll make the conclusion. Okay. So this is the whole idea of the design of experiment actually, or to check with the whether our methods are correct or not. So what is the actual objective of the experiment we can say? So experiment actually, so the so first objective is something we tell, determining which variable is going to more influence on the response. I told like we have input, we have the block backs, got the black box, some factors are there, then output. So it's a y. Okay, response y. This some control factor, uncontrol factor. So now we have to decide like which factor is going to more response on the y. If we change one factor, that the what will happen to the y output. If we change another factor, what will happen with the output and all. Then determining where to set the influential x is like something called optimum value of x, so that we'll get the y will be the desired value. Okay, determining where to set the influential of the x optimal, y desired, what the error should be less. Error should be less. Determining where to set the influential xs so the effect of the controllable variable are minimized. We'll try to make as x as an optimal effect of uncontrolled variable. It should be minimized. So that's why some of the other factors that objective is to always we should have desired output. But the thing is that factor should be as much like optimal value. I'm not saying that the minimal or the maximum, it should be optimum value. Optimization. That's why the term will comes when we talk about that statistic and all, that will say optimum parameter and all. Optimal parameters will comes into the picture. So it's just something improve the process yields, reduce the variability, and then reduce the development of the time and reduce the overall cost of the whole process. For whole process, we have to reduce the overall cost also. Okay. So that is the idea, like what is the purpose and then what is the objective and all that we have to see out. So if we talk about, so what are the types of the statistic design of experiment is there? First one we call statistical design of experiment. First one we call randomization. In that also we have CRD, RCBD. So RCBD will come here also. It's a randomization control blocking system. CRD is complete randomization design of experiments. Okay. Then we have the RCBD. Then we have the replication. Replication is something we call we are going to make the experiment again and again, again and again. Blocking will make a similar variable will block at one place, homogeneous blocking will do and will do. So statistical approach to the experiment design when we are going to draw a meaningful conclusion. The data involves the error. So in that we can do the analysis and all. So if we talk about that the randomization, it's a cornerstone underlying the use of a statistical method on. So in that we mean the both the allocation of the experimental material and the order in which run the experiment are to be performed are randomly determined. So first one what we are going to make it like A, B, C, D. 1, 2, 3, 4. 2, 1, 3, 4. 4, 1, 2, 3. Something that we have to randomize and all. So we have to do everything in the random order. Then what we have by replication. Replication we mean the independent repeat run for each factor combination. Something that we are going to make repeat, 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 repeat. Okay. So then we have the blocking. Blocking is actually improve the precision with which comparison of the factor are to be made. Blocking is actually used for the reduce or eliminate the variability transmitted from the nuisance factor. Nuisance factor is something called uncontrollable. Okay. So what are the guidelines of the experiments? First, we are going to recognize an statement of the art of problem. This is a pre-experimental planning. Then what we have selection of the response variable. We'll check what are the variables that will come into the picture. Then we'll check with the what are the factor, level or ranges will be there. So it's something that we have to all design before the experiments. We have to think. Let's say I'm going to say drug cancer treatment. So for that, we have to design what is our purpose, or what is the state of the statement of the problem. First step. Second one, what will be what will be the response variable? Whether I have to check with the efficacy of the drug, it should become more improve and all. So that we have to define. Then we will check what is the factor or level, all the ranges will be there. It's like something that controllable factor will be there. After that, we have to design the experiments. Like which experiment need to be go? RCBT, replications, blocking and all. Or we have to go with the factorial design, or we have to go with the other methods and all. Then after we have to perform the experiments. Once we collect the experiments, now we'll come to the statistic. We have to do the data analysis. So in that also we have seen many methods are there. It is test based upon that the groups, or maybe ANOVA or two-way ANOVA or F test, chi-square test, and all that will do. Then based upon that we are going to make some sort of recommendation or something inference. So that is the whole idea of design of experiment that we have to see out. And that should be if any of the experiment and something that we took, if there is no difference came before and after of the experiments, so what will happen in that case? Like that we have to again run the experiments. Again, we have to design the experiments, or we have to change the experiments. If there is no much significant differences are there, or not. If there, so we okay that the results came good, so we can go ahead with that. If the results are not okay, so we have to again come back and then do. So now we'll see that the randomized complete block design. Before that, we were having CRT. Just 1 minute. Can you please tell that my voice is audible?
Yes, sir, it's clear.
Any doubt is there? So you can ask.
It's clear, sir.
It's fine, na? Okay, so in the randomized complete design and all, like it's something called RCBT, something called RCBT. In that, we are going to like we'll check with the Nugent's factor. So that the probability and effect on the response, but we are not interested in that effect. So variability will going to arise. It's a Nugent's factor. So, but the thing is that they're going to affect the response, but we are not going to. We don't have the interest. So that is what we call uncontrolled. It's a randomized is actually an extension of the pair t-test. What we'll do, we are going to check with the more than two level or more than two treatment that we have to do it. It's a technique such a lurking of the Newton factor, something like reducing F. So in that case, what we're going to do when that the Nugent's source of the variability is known and controllable, a design technique called blocking. Let's say we have something that some factor is coming close or that the error. If we are able to identify or we can control it, so we can do the blocking and systematically we can eliminate the effect of that the Nugent's factor. If not control, what will happen? The variability going to increase, so it's going to inflate the error variance, making it hard to detect the treatment differences and all. Because when we say that one TB, that the medicine we have, we took one treatment, second treatment, third treatment, fifth, fourth treatment, and we took number of samples many times. If we don't do the blocking and all, there might be a chances like that the nuisance factor will be more than we can inflate the error. Okay. So what to do? We have to do the blocking. We'll take similar parameter in the one group and we'll do it. So what is the blocking principle? Group experimental into a block that are going to be relatively homogeneous. It means similar properties. Within each block, compare all treatments. Like we'll take, let's say it's a block one, two, three, four. Treatment one, treatment two, treatment three. One, two, three, four. Then again we are going to randomize it. Like it should come in the all block also. Then complete means all treatment occur in the all block. All treatment, all treatment should occur in the each block. One, two, three, four. That happened for the all block. It should T3. So one, two, three, two, one, three, three, one, two. Then something like this we have to talk about. Okay. So it should come. Randomized, it should be done randomly. It should not be have any order, a specified order and all. It should not be like this. So we can see here, we have the block 1, block 2, block 3. 1, 2, 3, 4. But here, again, we randomized and all. Treatment, but the factor of interest like fertilizer, drugs, methods. Block is something, nuisance factor of the variations like soil, subjects, or time period. That will do. That we are not much worry, like will until and unless if we don't talk about the interactions, until and unless if we don't talk about the interactions, so this will behave like a nuisance only. So what will the total number of units that treatment, that the number of treatment into block. So we have one, two, three, four, four number of treatment into three blocks. So total will be the 12. Okay. So this is the whole idea of RCBD and all. If you talk about the CRD is a complete randomized design. In that, we are not going to do the blocking. It's in that what will be there as it is that we took as the raw data. Will not talk about the blocking and all. So in that case, the chances of the error will be more. CRD call complete randomized. So there will be a no blocking. So that the chances of the error will be more because we are not able to eliminate nuisance error. So that's the idea. So what will be that the model, mathematical model, Yij, only two things will be the mu plus treatment plus block plus error. It's a overall mean treatment effect, then effect of block, then this will be the always there. So what are the assumptions of the observation will be the each block are independent, or that the error what we have the terms normal distribution and contribution, that's always we are going to follow. Treatments are randomly allocated to the units within the blocks. Okay. And that LT model, like no interaction should comes between the block and treatment. If it is going to come, it will come two-way ANOVA or the factorial design. So means in the case of RCBD, there will be no talk of interactions and all will be there. If it is going to be take place, it's coming under the factorial design or we'll go with the two-way ANOVA. Today we will just introduce the what are the interactions and all. So if we talk about, so same thing we have discussed last, like treatment, BJ and all. And so what are the sum of that the total square? It was summation of that IJ, like treatment and block, Yij square minus Gt square by n. Then now we have to check with the treatment sum square. T1 square plus T2 square plus Tn square by B, and block sum square B1 square plus B2 square by B3 square by 3 minus, it's called G square by n. GT, grand total. Grand total is something called, we are going to take summation of that. GT square by n. Then the similar way, that we have to make the ANOVA table and all. Degree of freedom will be the T minus, for the treatment, it's going to be T minus 1. For the block, it's going to be B minus 1. For the error, T minus 1 into B minus 1. Then the total, number of total unit minus 1. Similarly, we have to calculate the FT if we want to check with the treatment. Anyway, we are not checking with the block. Why? Because we are more interested into the treatment instead of going with the block. So in that case, that we have solved one problem also. So now we'll see why it is going to be a necessary. Why RCBT is going to be a necessary. Tell me why. That the idea is to, if in the design heterogeneity, it means differences can inflate the error variance. So to combat this by grouping similar into the blocks. So that the idea RCPT is to, we are going to reduce the, like some sort of that of error that is having, like, so that we can reduce it by converting into the block, randomizing the treatment within each block. Then we are randomizing random for each block that should go all that the setup should go, and then controlling the known nuisance factor, soil fertility, machine batches and all. But we don't have as much, because when I'll say what happened with the, when the soil got changed with the fertilizer, it's a interactions will come into picture. So it's that will go two-way ANOVA. Then RCVT is actually increase the precision, statistical power by reducing the unexplained variation. Unexplained, like something called that that the nuisance variables and all. Assumptions like that the similar way. So can we solve one problem similar way? What we have? We have the five blocks are there, is it? Then what we have? Four soil types are there.
Treatment.
Yes, please. So we will start from. Do you have any doubt? Like,
Okay, proceed, sir. It's okay. I can understand.
okay, okay. So now first step will be go grand total. It will be a summation of Yij total. It's a 50, 55, 52, 53, 48, 54 till 49. It came how much? If you do something, it will come 1010.5. And N will become how much we have? Four treatment, like four fertilizer, and five blocks are there. So 4 into 5, 20. Is it? And what we have the fertilizer, like treatment. A. So we'll check with the total. 50 plus 48, 47 plus 49, 46. It came to 40. Similarly, we will go with the B, 55, 54, 53, 56 plus 52, 270. C, 52, 50, 49, 51, 48. We have 250. D will take similar way. It's came to 55. So we'll take one page or two page actually. Okay, so now we'll go with the block total. B1, it's called, we'll tell T1, T2, T3, T4. So B1 will become 50, 55, 52, 53. 50, 55, 52, 53. So it came how much? 2, 1. Similarly, if you go B2, it will come somewhere 203. B3, it will come somewhere 199. B4, it will come 208. B5, 195. So now the first step is to calculate sum of squares total. It's called SST. Summation of Yij whole square minus G square by N. It's a G, grand total, GT square by N. If you do like all 50, 55, 50 square plus 55 square, 52 square, 53 square plus 48 square, my plus till 49 square minus GT square by N, 1015 whole square by N. How much we have? 1020. So this much how much it will come, that you will check it out. Then we'll go with the sum of squares of treatment. SSTR, summation of T I square by N, not N, block by N. T1 square plus T2 square plus 3 square by B, its number of block, minus grand total square by N. So T1, T2, T3, how much was that? We were having 4 T1, T2, T3, T4. So what we have, or the number of blocks that how much we have, 1 by 5, 240 square, 240 square, 270 square, 250 square plus 250 square minus by 220. Some value will come. Then sum of square of blocks, 1 by T summation of Bi square minus GT square by N, 1 by 4. How much we have? We have the total of 5 blocks are there. 210 plus 293 plus 199 plus 208 plus 195 square minus 1015 whole square by 20. Some value will get. So SSE will become what? SST minus SSTR SSBL. So SST, if you see how much we have, if I have the value, so it will come 51556.25. And if you check about the SSTR, it's something coming 530. No, sorry. It will come, it will come 52090 minus 51556.20. It came 533.75. And if you talk about the SSTR, I'll write 324.75. SSBL, it came 198.8. And if you calculate the error, so it came 533.75 minus 324.75 minus 190.8, 10.2. If you calculate the degree of freedom for treatment, it's a T minus 1, block B minus 1, error T minus 1 into B minus 1. T, how much we have? 4. So it become 3. Block, how much we have? 5. So it become, and so T minus 1 is to become 12. And what about the total degree of freedom? It's a T B minus 1. 4 into 5 into 190. So now we'll make the ANOVA table. First, you take the source. You have to go with the degree of freedom. SS, MS, then F. First one we have treatment, block, error, total. Treatment, how much we have? 324.75. Block 198.8. 10.2. 533.75. Oh, this will become SS. It will become degree of freedom. 3, 4, 12, 19. Then we have to take for the treatment only. So 324.75 by 3. It came 108.25. For this let it be. F, F, MSTR by MSE. For this error 10.2 by 12. It's a 0.85. So what we have 108.25 by 0.85. So some value will came. It's a calculated one. Now we'll go with the F tabulated at 3, 4 and 0.05. Some value will come. Similarly, we can calculate the R square. R square will be formula SSTR plus SSBL by SST. Incredible. I think till here it's clear now. Is it?
Yes, sir, very clear.
So now we'll go to the like that the Latin square design that the design. Now what the idea was to we were just blocking it, but now the idea is going to in the blocking we were controlling only one variable. That's called Newton's factor. If we have to control two variable, in that case we have to go through the square design. Latin square design is used when two source of Newton's variance is going to control simultaneously. So it's an extension of RCBT, which control one blocking factor. RCBT actually control only one factor. It's a Newton's factor. But here we have to control the two factor. So it will come. Row effect will also will take into picture and will take the effect of column also in addition to the treatment also. So means still we are not taking the interactions. We are taking the individual row, individual column, but not saying like one with the two. It's a among we are not going. We are just going individually only. So for that we have a Latin square design that will tell. So first one was the CRD. Then we came to the RCBD. Now we are going with the Latin square design. So the idea here we are not going to control any factor or any variable. Here we'll control one Newton's factor. Here we'll control two Newton's factor. So we can see here 4 by 4, 5 by 5, 6 by 6. So it means it's a P by P. P treatment, P row, P column. It's something it will be always in the square matrix only. So here we are going to do two restrictions on the randomization. So if you see in the case of that the puzzle, if you see the if you play the game and all, it will be always in the square matrix only. That's a perfect example of Latin square design. So Latin square are closely related to the which one? Popular puzzle called Sudoku puzzle that originated in the Japan. Norm like that is the Sudoku means single number in Japanese. The puzzle typically consists of 9 by 9 grid. If you see, I didn't took actually. So if you are just go with the what you can say that Sudoku that is the what they call Sudoku, you can see there. It's a additional 3 by 3 block content within it. Few of the spaces contain numbers, others are blank. That we have to fill it up. So it's something so it will become the 9 by 9 Sudoku puzzle, have 3 by 3 block, also contain each of the 9 integer reduces the large number of possible 9 by 9 to a similar, but still quite large number. It will come this much number. Like number of square will going to be the 6 into 10 to the power 21. I'll show you how it will go. If you see the standard Latin square, number of Latin square will become sizes. If we have 3 by 3, it will become either one Latin standard square only. If we have the 4 by 4, you can take the perfect 4 by 4 square only the 4. Now it becomes 56. 4 by 4, 3 by 3, and 2 by 2 will not take. Only 3 by 3. If you say the so that the question will come, so do 2 by 2 also a square matrix, but no, but will not take it because we have the square, no treatment, row, column. So we have 3. So we can't go with the 2 by 2. Why I told 3 by 3 only 1. I think hopefully it clear na like why I'm saying I can't go with the 2 by 2. Because when I'll say Latin square, it means 1 is the treatment. 1. Second one, row. Third one, column. So we have the 3. 3 means 3 by 3. We can't go with the 2. If we talk in the RCBD, okay, 2 by 2 can go because only one factor we are controlling, one treatment, one is the factor. But here we can't. So here 3 by 3 matrix here, then 3 by 3 matrix here. So total we can make possible of 4 Latin square, standard square. In the case of 5 by 5, we can make 56. And 6 by 6, we can make 9048. 7 by 7, we can make 16 lakh 942,000. 1, 2, 3, कह दे सकरा, जब 10 lakh, 1 crore 69 lakh 42,080 we can make. Just similarly, total number will become like it's infinite like that can go. So I think it's a clear that how we are going to define it now. So what is the statistical model for that? We in that RCBD we were having Yij. Now it come Ijk mu plus alpha I plus Tj plus beta k Ijk. Mu is the mean, alpha is the row, tau treatment, beta will be the column. Okay. So in that case, SST will become how? SS row, SS column, SSE plus SSTR. And degree of freedom will become P minus 2 into T minus 1 because we are going to take 2. Like something, I'll tell you how it will go. So that you can see here. SS treatment 1 by T or P because it's a always 4 by 4, 3 by 3, 5 by 5, either P or T, either way. 1 by P, summation of Ti square minus Gt square by N. What about the SSR? 1 by P, summation of rho 1, rho square minus Gt square by N. What about SSC column? 1 by P, summation of Ci square minus Gt square by N. So this came SSTR, SSR, SSC. So how can we calculate SSE, SST? SST how we calculate? Summation of Yijk minus Gt square by N. It's a grand total. SST minus SSTR, SSR, SSC. Then degree of freedom for the treatment will become P minus 1. For rows, P minus 1. Column, P minus 1. But for error, it's a P minus 2 into P minus 1. This is stand for this one. And this P minus 2 stand for combination of this. Okay. So we are going to take two nuisance factor. Then what about the total? Total will become P into P. How much? P square minus 1. So it's a P square minus 1. So I think it's clear. Shall we solve one problem based on this?
Yes, sir.
Okay. I think this is all are same only. Similar way. Total degree of freedom P square minus 1, P1, P minus 1, P minus 1, column P minus 1. But the error will become P minus 1 into P, that the P minus 2. So now what we have the problem of Latin square design. In that, we have the soil type and irrigation method. Okay. So what we'll do? We'll start with the what? Grand total. Is it?
Yes, sir.
Summation of 52, 15, 49, 50 plus 48, so on till 52. It came how much? Mm, I'll see. And now we'll go with the row total. R1. R1 will become 52, 49 plus 50, 48. It will come how much? 199. Similarly, I'll take R2. It came around, it came R2 188, R3 row 3 51 48 99 99 plus 52 152 plus 49 201, R4 46 54 100 150 202. Now we'll go with the column total. How come? C1 52 47 51 46 52 47 99 plus 51 150 plus 46 196. C2 49 45 90 94 98 142 150, then it came 196 50 50 100 199. C4 50 50 140, it came 199. I think it's clear. Now we'll go with the treatment.
Sir, one doubt, sir. This
Yeah, yeah.
row into column, you calculated, first one is from the column. When column came, you calculated a row total. How is
Like
that?
this is the row 1, R1,
Ah,
52 49 50
that is
48.
column only, no, sir.
No, no, this is row. This is row.
Ah,
And this is column.
yes, sir. Okay, okay, thanks.
I think now clear.
Yes, sir.
Now we'll go with the treatment total. P1 is actually a for A, is it? So for A, what we have 52 here, 54 here. How much? 52 plus 54, 106. 106 plus 153, 159 plus 50. How much came? 209. Is it clear? T1.
Yes, sir. Yes, sir.
So it came 209. T2 for the case of B. Again, we'll go. So for B 47, B 49, 47, 49 will come 96. 96 plus 50, it came 146. 146 plus 49. 146 plus 49. 195. Is it?
Yes, sir.
Similarly for TC, TD. So TC what we have? C here 51, C 45, so 199, 150, so 149, 149, so 2 not 1. No, 2 not 198. Again T4, 46 and 48. D, D. 46, 48, 94, 94, 96, and 140, 148, like 188. So now we are ready with the row total, column total, grand total, column that the grand total what we have 790 if we summation 52, 49, 50, 48, 47, 45, 46, 50, 51, 48, 53, 49, 46, 54, 50, 52. So it will come 790. So and what is the n? N will become 4 into 4, 16. So now we'll go with the SST. What is there? Summation of Yij and K square minus GT square by N. It means summation of 52 square plus 49 square, 50 square, 48 square plus 47 square plus 45 square plus 46 square plus 50 square plus 51 square plus 48 square and all. So it will come, some value will come. It will come some value. So if we check, so it will come 39294 minus 790 square by 16. So it came the value how much? I will just write it 287.75. Okay, so now we'll go with the SS treatment. 1 by P. P means the number of block or number of that column. Summation of TI square minus GT square by N. So 1 by 4, 209 square plus 195 square, 198 square, 188 square minus 790 square by 16. So if you calculate, I'll just write it SSTR how much it came. It's a 57.25. What about SS row 1 by P summation of RI square minus GT square by N. So 1 by 4. What is that? 209 square plus 195 square plus 198 square plus 188 square minus minus 790 by 16. Some value will come. SSR we have I think we have kept wrong 199, 188, 202. This is actually TR. Sorry, we kept wrong. We can see 209, 105, 198, 188. Is it? Both are same. SSR 1 by P summation of R square minus GT square by N. SSR will become 1 by 4, 199 square plus 188 square plus 201 square plus 202 square minus 790 square by 16. It came how much? 31.25. So similarly SSC 1 by P summation of C1 GT square by N 1 by 4. SSC how much? 196 square plus 196 square plus 199 square plus 199 square plus minus 790 square by 16. So we have calculated all. It came SSC 2.25. So now we have done with the SST, SSTR, SSR, SST. Now we'll go with the SSE. Is it? SST was 287.75 minus 31.25 minus 2.25 minus 57.25. It came 197. So now we'll calculate the ANOVA table. Source And we'll go with the SS, degree of freedom, MS, F. Source, first one is the treatment, row, column, error, total. What is that treatment? 57.25. Row, how much we have? 31.25, 2.25, 197, 287.5. Degree of freedom for the treatment become 3, 3, 3, and 4 minus 2 into 4 minus 1 will become 6, 236, and then PA square minus 1, 16 minus 1 will become 15. And treatment like which will become how much? 57.25 by 3, and for error 197 by 6. So now F will become 57.25 by 3 into 6 by 197. 3 into 26. So that some value will come. Similarly, we can calculate the F tabulated, and R square we can calculate like SSTR, SSR plus SSC by SST. Any doubt is there? And that calculation you can do at the later part, is it?
Yes, sir.
So I think that the Latin square that didn't clear na.
Yes.
So we'll go one more model is there. We have the Gracio Latin square design. Is it? It's a
Yes, sir.
it's a similar problem that we have seen. Like what we have, only things will comes into the picture. That the 1, 2, 3 and all, and then SST operator blocks SSTs are there. Only thing that will change with the Latin square A, B, C, D and all. So now we have the Gracio Latin square design. So what we were discussing till CRD, no, RCBD 1, then we came to the Latin square design. Now we came to the GSLD, GLSS, SD. 0 control, 1 control, 2 control. Now we can control the 3 vector, 3 vector. Is it? So mu, theta I, treatment, and this one. So you can see here 1, 2, 3, 4. A alpha. A is the one treatment, alpha is the Greek letter. It's come under the consider a p by p Latin square and superimpose on it the second Latin square in which we are having A, B, C, D, D, B, A, C. We are going to superimpose with the another Greek letter, alpha, beta, gamma, and all. Nothing is there. Whatever we have discussed in the Latin square, it's just to superimpose the one more Greek letter. Superimposed have the property at each Greek letter appear once only with each Latin letter. It's something that we have to do the one that Latin letter or Greek, that the Greek that the letter will go for the all. So the Latin squares are said to be the orthogonal. For both AB will become one. AB inverse will become the one, like orthogonal. And this sound obtained is called Gracio Latin square. No. So no symbol either from the square repeats in the any row or column. No pair of the symbol repeats anywhere in the square. This will allow three source of variation. One row, one column, and two treatment factor. So nothing will change. Everything is same. Only thing will be control of the variable will be more. So here, row will be the first blocking factor, column is the second blocking factor, Latin is that the letter is the primary treatment, Greek letter is the secondary treatment. So what will be the degree of freedom for this p minus 1, Greek letter p minus 1, p minus 1, and here's the p minus 1, but here p minus 3 and p minus will come. Okay. Only thing, nothing will change. Only thing will change. T minus 3 here, and SST will become summation of whatever I, J, K, L square minus grand total square by N. SSTR, it's a Latin treatment. 1 by P1 square plus P2 square till minus GT square by N. If we talk SS Greek, SSGR, 1 minus P summation of G1 square, G2 square minus of GT square by N. SSC similar way, SSR similar way, SSE will become SST minus SSTR minus SSGR minus SSC minus SSR. I think it's clear. Shall we solve one problem?
Hi, sir.
So here what we have? We have the 4 fertilizer, one treatment, 4 irrigation, second treatment, while field is the row, season is the column. So what we'll do? We're going to start with the what? Grand total. Summation of Y, I, J, K, L. 52, 49, 50, 48 till 52. It came grand total how much? I have to see. I think it's a similar value. If you see 52, 49, it's a similar value only. Only thing that the we just introduced the Greek letter, is it? Similar value only. Only that we it's a 79. No, 790 and 16. So we'll go with the row total. R1 will be same 199. R2 will be 188. R3 the 2 1 in. R4 will be 202. Column total C1 196, C2 196, C3 199, C4 199. So now we'll go with the fertilizer. Latin. Okay. So what we have, we'll say A summation A 52, 54, 53 and 50. How much it came? 209. Similar way. B 195, C 198, D 188. Now we'll go with the irrigation. What will be there? Alpha. Alpha, where is that? Alpha 52 here. And let's say this one will say alpha because it's a bit wrong. 52 48 100 and then alpha 46, alpha 49. It will come somewhere 203. Beta will come 196 and gamma will come gamma 47 here, 40 54 here, 50 here, and gamma will okay. Let it be like this only. It can go. So we can see here alpha alpha is there, so gamma is there. So we can gamma will come 201, delta will come 193. Okay, we'll take 2 page actually. 2 page will be enough. Okay. So how we will start? Start with the SFT. Is it? It came, how much it came, like 39294 minus 39,006.25, 287.4575. Then we'll go to the SSR, 1 by P summation of R I square minus GT square by N, 1 by 4. If we go 199 square summation minus 790 square by 16, it will come somewhere 31.25. SSC 1 by 4, column 196 plus 199 plus 199 square minus 790 by 16. It will come 2.2. Now we'll go with the Latin treatment. SSLT 1 by 4. Latin treatment was, how much was there? 209, 105, 108, 108. 209 summation of 105, 10 minus 790.16, 37.25. Now we'll go with the Greek treatment. SSG 1 by 4, 203 plus 195 square minus GT square 790 by 16. It will come 47.95 x75. Okay, so now we'll go with the which one? Error. SST, SSC, SSR, Latin treatment, Greek treatment. 287.25 minus 13.25 minus 2.25 minus 15 and 47.25. It came 49.75. Okay. So now we can calculate the ANOVA table. Is it? Source, which one? Row, column, Latin treatment, Greek treatment, error, and total. SS, degree of freedom, MS, F. Can I do it now? Or shall I do it?
Do it, sir.
Okay. And here R square will calculate like SSC plus SSR plus SS Latin design plus SS Greek treatment by SST. So how we could calculate similar way. So so that the Gracio Latin square design completed. So now what we have, it's a similar problem is there that will keep in the that you can see in the later part. So now the question will sometime what will happen na sometime that all the treatment that can't occur in the all experiments. So for that case that another case will be there. Let's say we have some sort of that design is there. this happen here, but it not happen here. Maybe some error, some fluctuations and all something. So that will say balance incomplete block design. So we have made the blockage, but it's a incomplete. Sometimes too many treatment per block. Sometimes what will happen like if they have some similar properties, so that we can't do. So in that case, we will going to omit that particular treatment. So use a smaller block with the balance limited. And then if we are having like we'll go with the ratio or the Latin square, so that the resource is going to be like more and more and more. So in that case, we can go with the efficient design with the fewer observation. So in the case of what we have done with the R square and all that we have done, and that with the SST and all. SST and all. So here it will come adjusted one. Why? Because some experiment or some blocks doesn't have fully experiments are there. Let's say, as an example, a chemical engineer thinks that time of the reaction for the chemical process is function of the time catalyst employed. Four catalysts they have applied. The experimental procedure consists of selecting a batch of raw material, pilot plant, and applying to the each catalyst. Separate run for the pilot plant, observing the reaction time. Because variation in the batch of the raw material may affect the performance of the catalyst, engineer decided to use the batch of the raw material as a blocks. However, batch is only large enough to permit three catalysts. Okay, so therefore, randomized incomplete block design must be used. Sometimes we'll be having some limitations. In that case, so we have to design like a BIBD. For that case, we have to calculate like it should be a balance. AR is equal to BK. R times plus B block. K will be the number of observations and all will be there. Lambda is a symmetric. So that the model will be same. Mu, treatment, block, and error. The only thing will change here, adjusted treatment will comes into the picture. That will calculate from the lambda here. Other things are same. Is it? So if you see here, we have the treatment adjusted. This is the formula. We have to keep K Qi square plus lambda A minus 1. That is same way. Same, same, same. Only thing will change in the SS treatment. Because what we have done, we didn't did for the square or whole the block we didn't did. Sometimes we have taken off because there's some sort of limitations were there. So therefore that we have to calculate the word. We have to calculate the adjusted SS treatment and all. So I think hopefully this is clear. On this basis, we'll not solve the problem actually. We'll go directly to the next problem. Is it?
Yes, sir.
So now we'll introduce like till now what we have discussed. We were discussing individually row, column, or maybe treatment, second treatment, third treatment, and all. But now, anyway, when it's something when we see, it's going to be dependent on the others. It's called interaction. Interactions occur when the effect of one factor depends upon the level of another factor. It means combined effect of the two factor is not going to be additive. It will come in the form of something called together. They influence each other, not addition and all. So imagine if that we are going to testing the factor A type of the fertilizer, organic versus chemical. Second factor we have irrigation level, low versus high. So only under high irrigation but not under low irrigation, there is an interaction between the fertilizer type and irrigation level. So now the concept of two-way ANOVA will comes into picture. Means organic is going to behave different with the low, organic with behave with the high. It's something we call interaction will, or they are going to influence each other. I think that the idea of interaction is clear. Is it?
Yeah, yes, sir.
So for that, we have to calculate that the model will be similar. Mu, alpha, beta, that is a similar way. But alpha, beta all together will comes into picture. That called interaction effect or interaction between the two. So if you see that example, in the real world, we have the agriculture. Fertilizer will be the integration or crop variety with the soil type. Manufacturing will be the machine type with the skills, temperature, pressure in the chemical yield, drug with the doses, treatment with the age group. It will have interaction. Education was like teaching method plus a student background. If any teacher or any student doesn't have the background in the CSC or coding and all, they can't play with the machine learning and all or in the coding and all. Similar way, treatment and age group for the kid, some different treatment will be there. For the young, different treatments are there. But for the case of old age, different treatments will be there. So that we will see some examples in the case of some what we can say bigger case chemical process that we have the temperature catalyst concentration in chemical reaction. The yield depends upon the factor A. Let's say temperature. Factor B concentration. At low temperature, increasing the catalyst concentration improve the yield slightly. At high temperature, the same increases cause a dramatic jump yield. It's something called interaction between the one low or high to the catalyst and all. It will change. So it's something called interaction among the variable. Similar will that if you see the agriculture, fertilizer and that is the irrigation. Crop yield is influenced by factor A will be the fertilizer type, organic or chemical. If we have the farmlands are there, if you use the fertilizer like chemical or organic, it will change what will happen with the low and high. Organic fertilizer will perform under low irrigation. Chemical fertilizer will perform but better the high irrigation. It's a something called interaction. Then we have the drug and dosage. Patient recovery depends upon the factor A, that's a drug A, drug B, high doses, low doses, or drug A, drug B, it's some different compositions and all. Drug A works better with the low doses, it's an interaction. Drug B only shows effect at high doses, it's again a interaction. If you see that the comfort study temperature and humidity. If you are sitting in the AC, factor A is the temperature like high and low. Humidity is low and high. At low humidity, increasing the temperature will improve the comfort. At high humidity, that the same temperature increases the reduce the comfort. Temperature increase will reduce the comfort. So I think that the idea of interaction is clear, is it?
Yes, sir.
So based upon that, we'll go to two-way ANOVA. Before introducing the two-way ANOVA, we have to see what are the factorial design, how we can design it. Then we'll go with the statistic and all. So till today, whatever we have discussed, we'll solve some problems like 10 to 12 problem. Then we'll that the wind up to today. So just to 1 minute, I think. Okay, just tell me like which of the following is a key reason to use that use a randomized complete block. Just read it and try to explain.
E answer, sir.
Okay, can you tell the explanation or more?
Nuisance.
Okay, what
Like,
are, what can be the reason?
maybe it
That
can
the
be soil, good fertility soil, or it
yeah.
can be, in case treatment, it can be something noise or age factor.
Hmm. So that the RCB that so that the RCBD idea is to what is the idea to reduce the nuisance factor that we don't have the control over it. Is it? Second option will see no that the first option to reduce the number of treatment required. No, that number of treatment will be same. Is it?
Yeah, yes, sir.
Number of treatment will be same only. The only idea is to control the variability in the experiment. What is the third option? To Randomize the order of treatment because it's a randomization that is the part of design, not the key reason. Is it?
Yeah.
What are the fourth one?
It's the interaction
That the interaction. I like in the case of RCBD and all, there will be no case of interaction will be comes into the
interaction.
picture. So that the interaction will come only when we'll go with the two-way ANOVA and all. Is it?
Yes,
So
sir.
for the first question, we have the answer of B. Now we'll go with the second one. In a randomized complete block design RCBD, the total variation is divided into how we are going to divide SST or that the model for RCBD. What is that? Tell me. Yij is
Answer
equal to
A.
mu plus
Mu.
alpha beta plus ij.
Absolute.
So it means mu is
Treat
the overall mean treatment block
the
error.
error.
So this is the correct option. Treatment and block error will be always there. Block and error, there should be a treatment. Treatment block interaction. So there should be no interaction. Is it?
Yes, sir.
So we can see here SS treatment, SS block, SS error. No treatment and block will it's going to what you can say violate the RCBT design. In a Latin square design, how many treatment can be used if there are four rows and four columns? I have shown
Four.
one
Yes, sir.
table in the case of 3 by 3 1, 4 by 4 4. In the case of 5 by 5 it becomes 56, is it?
Four. Yes, sir. Four on
It's
the
it
scales.
4. We can see here it's a P by P arrangement. It's a P row, P column, P treatment. Rule that the number of treatment equal to number of row, number of column. Each treatment appears exactly once in each row, once in each column. So if row 4, column 4, so treatment will be also 4 only. We can see here row, column 1, 2, 3, row, column, then treatment A, B, C, D, B, C, A, D, C, D, A, B, D, A, B, C. That's the four possible cases. What are the assumptions about the block effect in the RCBD? Can you tell? What are the assumptions about the block effect in the RCBD? They are saying assumptions of the
Random.
RCBD, not it's saying specifically for the block.
Random, sir.
No,
No.
assumptions of the RCBD about the block. So block will be the always fixed. We have to fix the block now.
Uh,
That is the random. Random is the part of design of experiments. Is it?
yeah.
The only thing that treatment is going to be random. Is it? One, two, three, four we have done. That the
Yes.
treatment A, B, C, D, this will vary. Is it?
Yes, sir.
So this can't be. They interact with the treatment effect. No, there is no
No
interaction.
interaction.
They are independent of the treatment effect. No, it's going to depend na.
Each row and each column.
Yeah. So first option is the
It's
correct option. RCBT block are introduced to control the nuisance variation like soil fertility, machine and all. Assumptions like do not interact with the treatment effect. Block are treated to fix and removing the block variability so the treatment comparison become more precise and all. It's clear.
yes, sir.
Now, what is the blocking factor used in the RCBT? Similar question. Why is the blocking factor are used in the RCBT. So the idea of RCBT is to reduce the variability, is it? So to control the random variability in the experiment problem,
Variability.
yes. To reduce the number of treatment, no, it's a fix. Whatever we have done, we can't change now.
Yeah.
To randomize, it's a assumption of
So,
RCBT, not for the blocking.
okay.
To increase the variability between the treatment, no, it's a opposite.
Control. Yeah.
It's actually going to reduce the
Reduce.
variability. So I think that the blocking factor that is okay. In the randomized nuisance variability make a difference. Homogeneous block will make into the group. Homogeneous group will make into the group. So that will be going to be block is going to be minimized. It will increase the precision means that efficiency of the model, and we can control the nuisance factor and all. So shall we go to the next question?
Yes, sir.
In what type of situation is RCBT particularly useful?
B answer.
Which one?
B.
Just think about that RCBT that we are doing grouping for the similar or homogeneous group. Is it?
Yeah.
Just tell me like how come it can go. When there is a significant variability, is it?
Yes, sir. That will,
When
yeah.
yeah, when all experimental units are homogeneous, so we can go with the CRD. Then we don't need to do the blocking, is it?
Yes, sir.
It's a no need of, because it's already saying they are the homogeneous. So this can't be. When the number of treatment of the very large, it's okay. It's large or low, that we don't think much. RCBT can we can apply, is it?
Yes.
When interactions between the treatments are expected, no, there is no concept of the interactions will comes under the picture, is it?
Yes.
So we can't go. So RCBT is actually for the block effect. If all experiments are homogeneous, CRT is sufficient, no need for blocking. RCBT is most effective when large variability among the block or but homogeneity with the block. RCBT assume no treatment, no block interaction. Is it?
Yes, sir.
So that is this part is clear. Now a Latin square design control how many nuisance variable? How much? We have start
Yes,
CRT,
sir. Yeah.
RCBT, Latin square design. Then
Three years.
Gracio, how much?
Three,
No, 0,
sir. Yeah.
1, 2, 3. RCBT, 1 will be the nuisance factor plus treatment. Treatment
Yeah.
plus 1 nuisance factor.
One is
Here,
expected.
treatment plus row plus column. Here, treatment Latin, then
Four, four.
Greek. No, 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 3 only.
Three only. Yeah.
Greek treatment plus row plus column. So this will act as a only one. So
Yeah.
1, 2, 3.
Two,
So here
three.
only two. No, no. Row and column will only one. So CRT will be control the one. 0. RCBT 1. That is going to that LSD 2. GLSD 3. Is it?
Yes, sir.
So this option will be 2.
3, 2 only.
Yeah.
So row and column only one system.
Yeah, yeah. Row and column will count as a only one.
Okay, okay.
No, no, no. Just say
Ah,
treatment is alone. So we are
ah,
controlling two nations. So that is one is the row alone, column alone.
ah.
So two factor we are considering.
Okay, okay.
RCBD only one nuisance factor. Treatment is
Yes,
the
sir.
treatment effect we have to calculate. So it's the main character. But we are
Hmm.
controlling the one nuisance factor.
Yes.
But in the case of Latin, treatment is the main, but we are taking two factor to control alpha and beta, like it's a row and column. But in the case of that the ratio, that the treatment, Latin treatment will be same. Only thing we are taking Greek one, two, three. Is it?
Hmm. Yes, sir.
Yeah, don't get confused because I also got confused. Okay, so similar way, CRD, no nuisance variable controlled because it's already homogeneous. RCBD, we can control one nuisance variable. Latin square design, extend to the two row effect, column effect. Each statement appears only one row and column. If more than two nuisance factors are need control, so Gracio Latin square that we have to use it. Similar way what I explained, is it?
Yeah, yes, sir.
Okay, so now we came to the Gracio Latin square design in an extension of Latin square that allows for how much? Control of two additional nuisance factor.
Yes.
No, no.
Yeah. A.
Okay. Control of none one additional factor. It's called Latin square design.
0.
Is it?
Ah.
Then reduction in the number of treatment? No. Always fixed.
Yeah.
Inclusion of interaction term? No.
No.
It will come
ANOVA.
factorial design or two-way
Today ANOVA.
ANOVA. That will discuss in coming. So ninth one. Which of the following are the advantage of using the Latin square design? What is the purpose of the Latin square design? LST,
Yes.
they will take treatment plus two factor will consider. Is it?
Yes.
Control two source of variability. Yes. Randomize the treatment of across. Yes, they are doing. Can be extended to the control for the three source of variability. Yes. How? In the case of Gracio, LSD, reduce the number of experimental unit required compared to the full factorial design. Maybe that concept we didn't discuss as such. It's part of factorial design. And in this case, we can actually reduce the number of experimental unit compared to the factorial design. Once we'll see the factorial design, that I will explain and I'll come back and then I'll explain this also. Okay. So it's a four, all are correct.
Correct.
So control two nuisance factor, that is the row column, still involve the randomization. Yes. Can be extended. Yes. Gracio. Gracio. Compared to the full design, LST is more efficient. Needs a few more because of full four treatment in full factorial with the three blocking factor would need far more than that of LST. That we'll see in the coming part. Okay. In Next class we'll see. So I think it's clear, this one.
Yes, sir. Clear.
So when we are going to use two-way ANOVA, there is a one factor with the two or more by the level, it's a part of one-way ANOVA, is it? One factor means one-way ANOVA. There are two factors with each two, it's a two-way ANOVA. There are three factors with the two or more level, it's called three-way ANOVA. There are two continuous variable, it's called regression, not the ANOVA and all. Okay. So second option is the correct. One way ANOVA, when we want to use compare means across the group defined by a single factor. Two-way ANOVA, we have the two factors, independent categorical variable, each with the two or more level. Let's say main factor, factor A, main effect of factor B, then the interaction effect. Then we'll be having three or more factor, it's a three-way ANOVA. When we have the two continuous variable, so we can use the regression or correlation will be the more appropriate compared to the ANOVA.
Yes, sir.
Then that we have one more in a factorial experiments, which of the following are true about the interaction effect. So they are asking more about the interaction effect. What do you mean by interaction effect? The effect of one factor depends on the level of another factor. It's correct only, but the thing is that when we talk in the factorial experiments, it's a F ratio is the correct answer. Okay.
Okay.
The effect of one factor depends on the other level of factor. That's also correct. Interaction effects are estimated by averaging all levels of the other factor. No. Why? Can you tell? It's a way of calculation. That's the way of calculation, like how it was calculated. Okay. Interaction effect are not important in the motion. No, it's a very crucial. Is it?
Yeah, yes, sir.
It's a very crucial. We have to consider it. Till now, we were discussing the ideal way. Row and column individual, another factor is individual. But in the real time application, what will happen? We'll be having the one will going to depend upon the other factor. So it's a very crucial. If we don't do it, they will not give the good results. Interaction effect will occur when impact of one factor depends upon the level on the factor. Another factor for the terms A and B. F ratio is actually used by. We'll come to the last question for the today. Which of the following are valid reason for using two-way ANOVA instead of multiple one-way ANOVA? Why? To account for the interaction between the factor? Is it? Yes. Because that the idea of two-way ANOVA it came because that interaction effect comes into the picture. Is it? Then to reduce the type 1 error rate when testing multiple factor. Yes. To estimate the factor of another while ignoring the other. No. The idea of two-way is actually to increase the number of level of the factor. No. Inflate the type 1 error. Two-way ANOVA, main factor of A, main factor of B, interaction effect. Running separate ANOVA, it's going to, we can't detect the interaction. That's going to inflate the error. Two-way ANOVA, not increase number of factor level. Just analyze the factor of level. Okay, so this can't be the answer. This can be the. So we have the two options is the correct. Is it?
Yes, sir.
So I think till here it's all clear.
Yes, sir. Today's class was very clear.
Okay, so next class or next session. So so now we are left with the two that the two more week. In that 2 week, we will discuss like more of factorial design, and this one factorial like to the power 2 factorial. Then we'll come to the ANOVA. And on the 14th, I will take one special session that I will start briefing from the first week to the last week. Like I'll give full sort of recap. So effectively, we have three session is the left out for this. So if you have any doubt, please ask. Okay.
This class was clear, sir. So any doubt is there next week I shall ask.
Okay. Okay. Thank you.
So thank you so much, sir.
Okay. Thank you. Thank you so
Nice
much.
class.